The Sun is a nuclear furnace burning at 15 million degrees Celsius, releasing more energy every second than humanity has ever used. Yet the space around it is almost absolute zero. You're standing next to the largest fire in the universe, and still freezing. How is that even possible, and what does hot really mean? Today, we're going to unravel this paradox by breaking down how heat actually travels through space, exploring the materials that keep astronauts alive in the void, and revealing why the warmth of Earth is not the rule, but a rare exception in a frozen universe. To truly begin solving the mystery of why the Sun cannot warm the emptiness surrounding it, one must first dismantle and then reconstruct the very definition of temperature, which is a concept that we often take for granted in our daily lives on Earth. We frequently speak of the weather being hot or a cup of tea being cold, but research conducted by physicists over the last century has determined that these are merely human interpretations of a much deeper, invisible physical reality. Scientists have proven that what we perceive as heat is actually the frantic, kinetic dance of atoms and molecules. It is the collective energy of trillions of tiny particles bumping into one another like a crowded marketplace where everyone is rushing to find their way. In this microscopic world, the faster these particles jiggle, vibrate, and collide, the higher the temperature of the object becomes, whereas a cold object is simply one where the atoms have grown sluggish, moving with the heavy, tired rhythm of a slow-motion film. Furthermore, it is important to note that temperature is not an independent property of space itself, but rather a measurement of the energy contained within matter, which means that for heat to exist in a way that we can recognize, there must be a physical medium to act as the host for this energy. On Earth, we are surrounded by a thick, protective blanket of gas where every cubic centimeter of air contains approximately 25 quintillion molecules, creating a dense environment where every particle is constantly colliding with its neighbors. Because there are so many of these tiny messengers constantly sharing their motion, energy is distributed with incredible efficiency, creating the stable, ambient warmth that allows life to flourish and ensures that the temperature of your room remains consistent from one corner to the other. However, as one moves away from the surface of our planet and enters the deep reaches of the cosmos, the density of matter drops to a level that is almost impossible for the human mind to comprehend. In the vast interstellar void, there are fewer than 5 atoms for every cubic meter of space, a density so low that it makes the most perfect laboratory vacuum ever created on Earth look like a dense, impenetrable forest by comparison. It is this profound absence of matter that creates the first layer of our paradox. If there are no atoms to vibrate and collide, there can be no temperature in the way we traditionally understand it. Scientists believe that space is not cold because it possesses some active property of chill, but rather because it is a profound vacuum where energy has no home to settle into or be stored. It is a realm of non-temperature, a place where the sun's energy passes through like a ghost, unable to find anything to grab onto or to set into the frantic motion that we identify as heat. Consider the most recent data from the Parker Solar Probe, a mission by the National Aeronautics and Space Administration that, as of March 2026, has completed another record-breaking approach to our star. The probe has traveled through the corona, the outermost layer of the sun's atmosphere, where temperatures soar to over 1 million degrees Celsius, significantly hotter than the actual surface of the sun itself. Yet, a fascinating reality of this mission is that if a human were to reach out into that million-degree plasma, they would not feel the searing heat one might expect from such a staggering number. Because the plasma in the corona is so incredibly thin and the atoms are so far apart, the actual number of high-energy particles hitting your skin would be too low to transfer a significant amount of heat. This illustrates the fundamental truth of the cosmos. High temperature does not always mean high heat, because without the density of matter to carry that energy, the heat remains a theoretical potential rather than a felt reality. Moreover, the vacuum of space acts as the ultimate insulator, far more effective than any man-made material or double-walled thermos flask. On Earth, heat moves through three primary channels: conduction, convection, and radiation. If you heat one end of a metal rod, the atoms at that end begin to vibrate violently, eventually bumping into their neighbors and passing that motion down the line until the entire rod is hot. This is the process of conduction. Similarly, if you heat a pot of water, the warm fluid rises and carries the energy upward in a cycle known as convection. In the emptiness of the celestial expanse, both conduction and convection are essentially bankrupt because there is no physical bridge of atoms to carry the message of heat from the sun to the surrounding environment. This leads to a counterintuitive reality where a thermometer floating in the dark of space would not actually be measuring the temperature of the space around it, but rather the internal energy of its own materials as they slowly bleed away into the void. Without a surrounding medium to provide new energy through collisions, any object in space, be it a thermometer, a satellite, or a human being, would begin to lose its own heat through the only method left: radiation. Over time, the atoms of the object would slow down as they emit infrared energy, eventually settling at a point just a few degrees above absolute zero. Absolute zero, or 0 Kelvin, represents the theoretical limit where all atomic motion ceases entirely, a silence so deep that not a single subatomic particle shivers. Research indicates that the universe is currently permeated by a faint glow of energy left over from the beginning of time, known as the cosmic microwave background radiation, which keeps the floor of cosmic temperature at approximately 270 degrees below 0 Celsius. This is the baseline, the room temperature of the universe, and it is the reason why we perceive space as a freezing wasteland. Even though the vacuum itself is technically neither hot nor cold, one must also consider the strange behavior of materials in this environment of nothingness, where the rules of thermodynamics are stretched to their limits. Because a vacuum is such a poor conductor of heat, an object in space has a very difficult time cooling down if it becomes too hot, or warming up if it becomes too cold. It is much like being trapped inside a giant, invisible thermos that spans the entire universe, where your own body heat has nowhere to go. This creates a duality that is almost impossible to find on Earth. A single object can be both incinerated and frozen at the very same time. If an astronaut were to float in the void, the side of their body facing the sun would be bombarded by solar energy, causing their atoms to vibrate with such intensity that their tissues would begin to burn, while the side facing away into the darkness would be radiating its own heat into the infinite sink of the void, rapidly cooling toward those sub-zero baseline temperatures. There is no middle ground in a vacuum, no gentle air to whisk away the excess heat or to provide a buffer against the cold of the shadows. Scientists have determined that this extreme environment forces us to rethink the very nature of survivability, noting that it is not just the lack of oxygen that makes space deadly, but this total breakdown of thermal equilibrium. We are used to a world where hot and cold eventually mix to become warm. But in the architecture of nothingness, these two extremes exist in a permanent, violent standoff. It is important to realize that this emptiness is also what allows the sun to remain so hot for billions of years. If space were filled with air, the sun would lose its heat through convection and conduction almost instantly, cooling down like a hot coal dropped into a bucket of water. The vacuum, by refusing to be heated, acts as a protective barrier that keeps the sun's nuclear fire contained, allowing it to burn with a steady, terrifying intensity for eons. This realization shifts our perspective from seeing space as a hostile cold to seeing it as a protective silence, a void that preserves the energy of the stars by refusing to participate in the exchange of heat. The deeper we look into this void, the more we realize that our entire experience of life is predicated on the fact that we do not live in a vacuum, but in a rare pocket of somethingness where the rules of the universe are softened by the presence of an atmosphere. Yet, if the vacuum of space is so effective at preventing heat from moving through conduction and convection, it remains a staggering question of how that solar energy manages to find us at all. How does the sun's fire leap across 150 million kilometers of a wasteland that cannot be warmed? And what form does that energy take as it bridges the gap between the solar furnace and our fragile blue home? This brings us to the realization that the warmth of our world is essentially a gift delivered by the one thing that can ignore the vacuum entirely. The invisible, unstoppable messenger of electromagnetic radiation. To understand how the sun's fire reaches us through a wasteland that refuses to be warmed, we must explore the extraordinary nature of radiation, which is the only method of heat transfer in the universe that does not require a physical medium to travel. While we have already established that conduction and convection, the two ways we usually experience heat on Earth, are essentially bankrupt in a vacuum, radiation operates on an entirely different set of physical laws. If you were to think of conduction as a secret whispered from one person to another in a crowded room, and convection as the movement of that entire crowd, then radiation is like a laser beam shot across a dark, empty canyon. It does not need the air, it does not need the ground, and it certainly does not need the permission of the vacuum to make its journey. It is a self-sustaining wave of energy that carries the signature of the star that birthed it. Scientists at the National Aeronautics and Space Administration have determined that the sun's energy travels toward us in the form of electromagnetic waves, which are essentially oscillating ripples in the electric and magnetic fields that permeate the entire universe. These waves are made up of tiny, massless packets of energy called photons, which are born in the chaotic, high-pressure environment of the solar core. It is fascinating to note that a single photon can take tens of thousands of years to bounce its way from the center of the sun to its surface. But once it breaks free into the vacuum of space, it begins a sprint of incredible proportions. These photons travel at the cosmic speed limit of 299,792 kilometers per second, a speed so immense that it could circle our entire planet 7 times in the span of a single human heartbeat. At this velocity, the journey from the sun to the Earth takes approximately 8 minutes and 20 seconds, meaning that when you feel the warmth of the sun on your face, you are actually experiencing a touch that was sent from a star nearly 150 million kilometers away, before you even finished your morning coffee. It is important to realize that as these photons stream through the vacuum, they do not heat the space itself, because there is nothing there for them to collide with. This creates a hauntingly beautiful image of the solar system, a vast, dark gallery filled with invisible rivers of energy that are traveling with enough power to vaporize a mountain. Yet they remain silent and cold as they pass through the void. Have you ever considered that the space between us and the sun is filled with enough energy to power 1 trillion civilizations? Yet, if you were to stand in that stream without a physical body to catch the light, you would feel absolutely nothing. This is why the vacuum remains at 270 degrees below zero, even while being bombarded by the most intense radiation in the solar system. The light is simply passing through a room that has no walls to catch it. Furthermore, research conducted by the European Space Agency and the designers of the Parker Solar Probe has provided us with a new perspective on how this radiation is structured. We often think of sunlight as a simple, white glow, but it is actually a complex spectrum of different energies, including ultraviolet rays that can damage our skin and infrared waves that we perceive directly as warmth. Scientists believe that infrared radiation is the primary language of heat in the cosmos, as these longer wavelengths are particularly effective at causing the atoms in solid objects to vibrate. When an infrared photon finally encounters the atoms of our atmosphere or the surface of a planet, it transfers its momentum to those particles, effectively waking them up from their sluggish state. This transformation is the exact moment when light becomes heat. It is the point where the invisible messenger finally delivers its cargo, turning a silent wave into a frantic, microscopic dance of matter. To make this concept more relatable, think of a cold, still pond on a winter morning. If you throw a pebble into the water, the ripples travel across the surface without moving the water molecules very far from their original positions. The energy of the throw is carried by the wave itself. In the same way, the sun throws photons into the pond of the universe, and these ripples travel across the vacuum until they hit the shore of our world. On Earth, we are lucky to have a shore made of dense air and solid ground, which can catch these ripples and turn them into the warmth we feel. But in the deep void, there is no shore, no water, and no medium. Only the pebble and the infinite distance it must travel. This brings us to a compelling debate within the scientific community regarding the temperature of sunlight itself. While space is cold, the effective temperature of the radiation coming from the sun is nearly 5,500 degrees Celsius at the surface of the star. As this radiation spreads out into the vastness of the solar system, it follows what scientists call the inverse square law, which means its intensity drops off rapidly the further it travels. By the time it reaches the Earth, the energy has been diluted, but it is still powerful enough to drive our weather systems and sustain all biological life. However, if you were to travel further out, toward the orbit of Pluto or the Kuiper Belt, the sun would appear as little more than a very bright star, and its radiation would be so spread out that it could no longer provide enough energy to keep water from turning into solid ice. Recent observations from the James Webb Space Telescope, which is currently orbiting 1,500,000 kilometers away from Earth, have highlighted the extreme precision required to manage this radiation. The telescope must maintain a temperature of approximately 35 Kelvin, which is nearly 238 degrees below 0 Celsius, to detect the faint infrared signals from the first galaxies. To achieve this, it uses a massive 5-layer sunshield made of a material called kapton, which is designed to reflect the sun's radiation back into space. This shield is so effective that while the side facing the sun is hot enough to boil water, the side facing the telescope's sensitive instruments is cold enough to freeze nitrogen into a solid. It is a masterpiece of material science that proves we can manipulate the invisible bridge of radiation to create our own pockets of extreme heat or extreme cold, depending on which way we point our mirrors. One of the most awe-inspiring events related to this journey of light occurred during the solar storms of early 2024, when massive bursts of radiation and charged particles were flung from the sun's surface toward the Earth. These events, known as coronal mass ejections, remind us that the sun is not a static lamp in the sky, but a dynamic and violent heart that occasionally beats with extra intensity. When these bursts of radiation hit our magnetic field, they create the stunning displays of the aurora borealis, but they also serve as a reminder of how vulnerable we would be without our planet's natural defenses. The radiation that warms our skin is the same energy that, in slightly different forms, could strip away our atmosphere and leave us as barren as the moon. Scientists at the National Science Foundation have noted that the quality of the light we receive is just as important as the quantity The specific mix of visible, ultraviolet, and infrared light is what allows our plants to perform photosynthesis, while preventing the planet from becoming a scorched desert. It is a balance so fine that even a slight change in the sun's output or the Earth's ability to absorb that radiation could lead to catastrophic shifts in our climate. Furthermore, it should be noted that the sun is actually getting very slightly brighter over hundreds of millions of years as it consumes its hydrogen fuel, which means the invisible bridge is slowly becoming a more intense path of energy. As we ponder this cosmic connection, it is worth asking, what is it like to be a single ray of light, traveling for millions of miles through a silence that refuses to listen, only to find a home in the atoms of a single flower or the eyes of a child? It is a journey of profound loneliness that ends in a moment of intense connection. A bridge built of nothing that supports everything. We have seen how the vacuum acts as an insulator and how radiation acts as the messenger. But this still does not explain why the Earth remains a warm paradise, while its neighbor, the Moon, is a graveyard of temperature extremes. If the sun's radiation hits them both with equal intensity, why is one a garden and the other a wasteland? The Moon hangs in the silence of the void, just 384,000 kilometers away. A distance so small on the cosmic scale that both our world and its satellite essentially occupy the same room in the solar system. They are bathed in the same stream of solar photons, bombarded by the same invisible rivers of energy. Yet their fates could not be more different. On the lunar surface, there is no wind to carry the scent of rain, no clouds to soften the glare of the sun, and, most importantly, no atmosphere to act as a thermal buffer. Scientists at the National Aeronautics and Space Administration have recorded temperatures on the Moon that would be fatal to almost any form of life we know during the long lunar day, which lasts about 14 Earth days. The surface temperature can soar to 127 degrees Celsius, hot enough to boil a kettle of water simply by setting it on the ground. But as soon as the sun slips below the horizon, the heat does not linger. It vanishes instantly into the infinite sink of the void, causing the temperature to plummet to a bone-chilling minus 173 degrees Celsius. What is truly haunting about this 300-degree swing is that it happens without a single breath of air to announce the change. On Earth, we are accustomed to the golden hour of twilight, that gentle transition where the warmth of the day slowly fades into the cool of the evening. But on the Moon, there is no such mercy. If you were to stand in the shadow of a large lunar boulder, your feet could be freezing in the darkness, while your head, still poked into the sunlight, would be baking in the unshielded radiation of a nuclear furnace. This radical disparity reveals a fundamental truth about our own home. We do not live on the surface of a planet so much as we live at the bottom of a vast, transparent ocean of gas that serves as a planetary life support system. This ocean, our atmosphere, is a masterpiece of natural engineering that performs a task so complex it makes our most advanced spacecraft look primitive by comparison. It acts as a selective filter, a revolving door for energy that allows the right amount of light to enter, while preventing the resulting heat from escaping too quickly. When the sun's radiation strikes the Earth, it is not just the solid ground that reacts, it is the trillions of molecules of nitrogen, oxygen, and carbon dioxide that begin their own invisible dance. Furthermore, research conducted by the National Oceanic and Atmospheric Administration indicates that our atmosphere acts like a thermal sponge, soaking up the kinetic energy of the sun and distributing it around the globe through vast, circulating currents of wind and weather. Have you ever stopped to wonder why a cloudy night often feels warmer than a clear one? It is because the water vapor and carbon dioxide in our air are infrared active materials. They are tuned to the specific frequency of heat radiating back from the Earth's surface. Instead of letting that heat escape into the vacuum of space, these molecules catch the energy, vibrate with excitement, and then re-radiate it back down toward us. This is the greenhouse effect, a term often discussed in the context of climate change, but one that is actually the primary reason why the Earth's average temperature sits at a comfortable 15 degrees Celsius. Rather than the frozen minus 18 degrees, it would be without an atmosphere. We are, quite literally, living inside a planetary-scale insulation project that has been under construction for over 4 billion years. But the atmosphere's role goes far beyond merely trapping heat. It also involves the art of reflection, a concept scientists refer to as albedo. Imagine a world covered entirely in mirrors. It would be incredibly bright, but it would also be freezing cold because it would reflect all of the sun's energy back into the void before it ever had a chance to become heat. Earth, however, is a mosaic of different materials. The dark, deep oceans absorb nearly all the light that hits them, turning it into thermal energy, while the bright white ice caps of the Arctic and the fluffy tops of clouds act like mirrors, tossing energy back into space to prevent us from overheating. In the last 12 months, satellite data from the European Space Agency has shown a concerning trend where the melting of polar ice is lowering the Earth's overall albedo, meaning our cloak is becoming more absorbent and less reflective. A shift that is subtly altering the thermal balance that has remained stable for thousands of generations. Consider the sheer weight of the air above you at this very moment. Although it feels like nothing, there is about 10 tons of gas pressing down on every square meter of the Earth's surface. This pressure is what keeps our water in a liquid state, preventing it from boiling away into the vacuum. But it also creates the density required for heat to move through convection. On the Moon, a pot of water would not simmer. It would either freeze solid in the shade or explode into vapor in the sun. On Earth, the air provides the friction that slows down the loss of energy, ensuring that when you go to sleep at night, the world doesn't turn into a block of ice before you wake up. It is a slow, rhythmic breathing of a planet that knows how to hold its breath. Scientists believe that the presence of an atmosphere is the single most important factor in the search for habitable worlds beyond our solar system. In 2025, the James Webb Space Telescope turned its powerful infrared eyes toward a system of planets known as TRAPPIST-1. Located 40 light-years away, researchers were looking specifically for signs of an atmosphere on these rocky worlds. Because without one, even a planet at the perfect distance from its star would be nothing more than a scorched rock. They found that the presence of even a thin veil of carbon dioxide could make the difference between a world that is a frozen tomb and one that could potentially host liquid oceans. It makes one realize that warmth is not a property of the sun, but a negotiation between a star and the skin of a planet. But nature has a way of reminding us of our fragility through the most spectacular displays of physics. In early 2026, a series of massive volcanic eruptions in the South Pacific injected millions of tons of sulfur dioxide into the upper stratosphere. This event created a temporary sunshade of tiny particles that reflected enough sunlight to cause a measurable drop in global temperatures for several months. It was a vivid demonstration of how easily the thermal balance of a world can be tipped if the mix of gases in our air were just a few percentage points different. Our oceans could boil, or our continents could be buried under miles of ice. We are riding on a thin, blue line of gas that separates us from the absolute zero of the void. A boundary so thin that if the Earth were the size of an apple, our entire atmosphere would be no thicker than the apple's skin. Furthermore, it should be noted that the atmosphere also protects us from the high-energy garbage of the solar system. Every day, millions of tiny space rocks, or meteoroids, slam into our upper atmosphere at speeds of tens of thousands of kilometers per hour, Instead of hitting the ground like bullets, they rub against the molecules of our air, creating so much friction that they are incinerated in a flash of light. That heat is absorbed by the atmosphere, a final gift from a dying rock that adds a tiny bit of energy to our world. On the moon, these rocks hit with the full force of their momentum, turning the surface into a cratered wasteland and ensuring that any heat on the surface is constantly being disrupted by the impact of cosmic debris. As we sit in the comfort of our homes, feeling the steady warmth of a room or the cool breeze of an open window, it is easy to forget that we are actually passengers on a spaceship that is constantly losing heat to a vacuum that is nearly 300 degrees colder than we are. We are only warm because our spaceship has a self-healing, self-regulating hull made of nitrogen and oxygen. But what if you had to leave this hull? What if you had to step out into the architecture of nothingness we discussed earlier, where there is no air to hold you and no blanket to keep you warm? How does a human being, a creature of water and warmth, survive in a place where the sun burns like a blowtorch and the shadows freeze like liquid nitrogen? As we look up at the moon, a silent witness to our planet's warmth, we begin to realize that our own lives are cradled by a fragile blue boundary of gas that we rarely stop to appreciate. But have you ever considered what happens when a human being, a creature composed mostly of liquid water and fueled by a constant internal furnace of 37 degrees Celsius, steps out from under that protective cloak and into the unshielded reality of the cosmos? This transition is not merely a change of location. It is a violent entry into a realm where the laws of thermodynamics, as we understand them on Earth, seem to splinter into terrifying extremes. To step outside the hatch of a space station is to enter a world of absolute sensory and thermal contradiction. A place where you are no longer a resident of a planet, but a solitary island of matter floating in an ocean of nothingness. Within the vacuum, you are immediately caught in what scientists often call the dance on the razor's edge, a state of existence where the difference between being incinerated and being frozen solid is measured by nothing more than whether you are standing in the direct glare of the sun or the velvet shadow of your own spacecraft. To understand the sheer scale of this hostility, one must look at the data recorded by the National Aeronautics and Space Administration during extravehicular activities, which show that an astronaut can experience temperature swings of over 500 degrees Fahrenheit, or approximately 260 degrees Celsius, in the span of a single step. Imagine for a moment that you are standing in a doorway where the air in front of you is a furnace at 121 degrees Celsius, hot enough to bake bread, while the air behind you is a freezer at minus 157 degrees Celsius, which is cold enough to turn oxygen into a liquid. This is the daily, grueling reality of the men and women who maintain our outposts in the dark, a world where there is no room temperature and no middle ground. Furthermore, it is important to note that the primary challenge of surviving in this environment is not actually the external cold of the vacuum, as many might assume from watching popular science fiction films where characters freeze instantly into blocks of ice. In a striking reversal of common sense, the greatest threat to a human being in space is actually overheating, because the vacuum is the ultimate insulator, lacking any air molecules to carry heat away through conduction or convection. Every watt of energy your body generates through its own metabolism has nowhere to go. You are essentially a walking, talking thermos flask. Your heart beats, your muscles move, and your brain fires electrical signals, all of which produce waste heat as a byproduct of existence. On Earth, the air around you constantly wicks this heat away. But in space, you are thermally trapped. Researchers have determined that a human body at rest produces about 100 watts of heat, roughly the same as an old-fashioned incandescent light bulb. But during the physical exertion of a spacewalk, this can jump to over 500 watts, without a sophisticated way to shed this energy. A person would succumb to heat stroke in the middle of a frozen void in less than an hour, their own internal fire becoming their executioner. To combat this, the engineers of the National Aeronautics and Space Administration and their international partners have had to invent what is essentially a microplanet that fits inside a garment, beneath the bulky, white outer shell of a modern spacesuit lies the liquid cooling and ventilation garment, a piece of clothing that represents one of the most remarkable achievements of material science in the 21st century. This garment is woven with over 90 meters of thin, flexible plastic tubing that rests directly against the astronaut's skin, acting like a synthetic circulatory system. A constant stream of chilled water is pumped through these tubes, absorbing the excess body heat and carrying it away to a specialized heat exchanger on the astronaut's back. Research shows that without this active cooling, the internal temperature of the suit would rise with every breath, eventually turning the life support system into a mobile oven. As you listen to this, imagine the sensation of hundreds of tiny, cold rivers flowing over your skin, a mechanical mimicry of the way our planet's oceans distribute heat from the equator to the poles. But how does one get rid of heat when there is no air to dump it into? The answer lies in a process called sublimation, which is a phase change that bypasses the liquid state entirely. In the life support backpack, a specialized device called a sublimator allows a small amount of water to turn directly from a solid ice into a gas in the vacuum of space. This phase change absorbs a massive amount of thermal energy, which is subsequently vented out into the void as harmless vapor. It is a slow, controlled sweating of the machine, a technological version of the way our own skin uses evaporation to keep us cool on a humid afternoon. One might find it poetic that to survive the absolute cold of the universe, we must carry a small piece of the Earth's water cycle on our backs, using the physics of ice to protect ourselves from the fire of the sun. It is a reminder that even in the most alien environments, we remain tethered to the basic physical laws of our home world. While the cooling system manages the heat from within, the outer layers of the suit must handle the terrifying radiation from without. A modern spacesuit consists of over 14 distinct layers of material, each with a specific role in the thermal defense of the human inside. The outermost layer is typically made of an orthofabric blend, including materials like Kevlar and Nomex, designed to be fire-resistant and tough enough to withstand the impact of microscopic dust particles traveling at thousands of kilometers per hour. Beneath this skin are multiple layers of aluminized mylar, a thin, crinkly plastic that acts as a series of mirrors. These mirrors reflect the sun's infrared radiation back into space before it can penetrate the suit, working much like the multi-layer insulation we discussed earlier in the context of satellites. It is a fortress of reflection, ensuring that even when the sun is beating down with enough power to melt lead, the person inside remains at a stable, comfortable temperature. The most iconic part of this thermal armor is, of course, the helmet, specifically the gold-coated visor that astronauts lower when facing the sun. This is not a fashion choice. It is a critical piece of radiation shielding that utilizes one of the most unique materials found in nature, because gold is one of the most efficient reflectors of infrared light in the universe. A thin layer of genuine gold, often just a few atoms thick, is applied to the visor to act as a one-way gate for energy. It allows visible light to pass through so the astronaut can see their work, but it reflects 97% of the sun's thermal radiation. Research conducted during the recent Artemis lunar missions in early 2026 has confirmed that this gold barrier is the difference between a clear view of the lunar horizon and having one's retinas scorched by the raw power of a nearby star. Have you ever wondered what it feels like to be inside this suit? Suspended between the two greatest extremes in nature, astronauts have described the experience as being thermally isolated in a way that is profoundly lonely and slightly surreal. You can feel the hum of the pumps and the chill of the water against your chest. But you are completely disconnected from the temperature of the world outside. You can reach out and touch a handrail that has been baking in the sun for hours, reaching temperatures of over 100 degrees Celsius. And because of your pressurized, multi-layered gloves, you will feel nothing but the resistance of the fabric. It is a state of existence where your senses are lied to by technology for your own protection. A constant reminder that we were never meant to leave the gentle, warm embrace of our atmosphere. Furthermore, scientists have determined that the psychological stress of these temperature swings is just as significant as the physical danger. In the shadow of a space station or a lunar crater, the darkness is so total and the perceived cold so absolute that it can trigger a primal fear of the void. Yet, even in that darkness, the astronaut is technically warm inside their suit, protected by the heat of their own heart. This disconnect between what the eyes see and what the body feels is a testament to the mastery of material science. But it also underscores the fragility of our position in the cosmos. If a single pump were to fail, or if a small tear were to occur in those 14 layers of fabric, the dance on the razor's edge would end in a matter of seconds. As we look toward the future, specifically the planned permanent moon bases of the late 2020s, the challenge of managing heat becomes even more complex. In the lunar South Pole, where the sun sits low on the horizon, shadows are incredibly long and can stay at -230 degrees Celsius for billions of years. These permanently shadowed regions are some of the coldest places in the entire solar system, yet they sit just a few meters away from ridges that are constantly bathed in sunlight. Future lunar habitats will need to be masterpieces of thermal engineering, perhaps using the lunar soil itself, a material called regolith, as a natural insulator. Because regolith is essentially ground-up rock with no air between the grains, it is a poor conductor of heat, making it an ideal material to pile over a habitat to keep the internal temperature stable. Scientists believe that the lessons we learn from keeping humans alive in these 500-degree swings will eventually help us build better, more efficient cities on Earth. The materials we develop for spacesuits, reflective coatings, phase change insulators, and advanced cooling systems, are already finding their way into our firefighting gear, our medical equipment, and our sustainable architecture. We are learning how to live in the extremes of the vacuum so that we can better preserve the Goldilocks environment we already have. It is a cycle of innovation where the hostile cold of space teaches us how to cherish the warmth of home. But if humans need 14 layers of high-tech fabric and a backpack full of ice to survive a few hours in the sun's glare, how do we build machines that can survive for decades? How do we create eyes like the James Webb Space Telescope that must peer into the birth of the universe while sitting in a place that is almost as cold as the void itself, yet still manage to be perfectly aligned and functional? To build a machine for the deep void is to engage in a constant battle against the 150 million kilometers of invisible energy that the sun pours into the solar system every single second. On Earth, we are used to materials that feel solid and reliable. But in the vacuum of space, those same materials can betray us. Metals can fuse together in a process called cold welding. Plastics can become brittle and shatter like glass. And simple lubricants can evaporate away into nothingness. Therefore, the selection of materials for a spacecraft is not just an engineering choice, but a high-stakes calculation of survival. Scientists at the National Aeronautics and Space Administration and the European Space Agency have spent decades perfecting a library of space-hardened substances that can handle the violent transition between the fire of the sun and the frozen silence of a shadow. The most visible and perhaps most critical of these materials is what is known as multi-layer insulation, which is the shimmering, golden or silver foil that you see wrapped around almost every satellite and lunar lander in photographs. It is important to note that this is not a single sheet of metal, but a complex sandwich of up to 40 individual layers of a specialized plastic called kapton or mylar, each one thinner than a human hair and separated by tiny, non-conducting nets. Research indicates that the primary purpose of this material is to disrupt the only way heat can move through a vacuum: radiation. By stacking these reflective layers, engineers create a series of thermal speed bumps where each layer reflects 99% of the incoming infrared energy back toward the sun. By the time a photon tries to fight its way through all 40 layers, its energy is so depleted that it can no longer warm the sensitive electronics hidden deep inside the spacecraft. It is a masterpiece of passive thermal control that allows a probe to sit in the direct glare of the sun while its internal computers remain at the same temperature as a comfortable spring afternoon. But why is so much of this insulation golden in color? This leads us to one of the most fascinating intersections of chemistry and physics in the modern era. While silver is technically a better reflector of visible light, gold is the undisputed king of reflecting infrared radiation, the specific wavelength of energy that we perceive as heat. Scientists believe that the atomic structure of gold, with its dense cloud of electrons, makes it almost impenetrable to heat-carrying photons. In the case of the James Webb Space Telescope, which is currently stationed at a point 1,500,000 kilometers away from our planet, gold was chosen to coat its primary mirrors not for its beauty, but for its cold, hard efficiency. A layer of gold, just a few hundred atoms thick, was applied to 18 hexagonal mirrors made of beryllium, a metal that is lighter than aluminum but stronger than steel. This combination allows the telescope to catch the incredibly faint infrared whispers from galaxies that formed over 13 billion years ago, while simultaneously reflecting away the heat of our own sun. Furthermore, it should be noted that the use of beryllium is a story of material wizardry in itself. At the temperatures required for deep space observation, which are often as low as -233 degrees Celsius, most metals will warp, shrink, or crack, ruining the precise focus required to see across the universe. Beryllium, however, has a unique atomic lattice that remains remarkably stable in extreme cold, ensuring that the telescope's eye remains perfectly sharp even as it sits in a deep freeze that would shatter a diamond. One might think of these materials as the immortal skin of our mechanical explorers, designed to endure a journey that no biological organism could ever hope to survive. However, reflecting heat is only half of the challenge. A spacecraft must also deal with the heat it generates internally. Just like the astronaut in the spacesuit, a satellite is essentially a high-tech thermos, and its own computers and batteries can produce enough heat to fry their own circuits if that energy is not managed. This is where the radiators come into play. If you look closely at the International Space Station, you will see large, white, accordion-like panels extending away from the main modules. These are not solar panels, they are thermal radiators, because there is no air to carry heat away. These panels must rely on the process of emission, using a specialized white paint called Z93 that is designed to be black in the infrared spectrum. This means that while the paint reflects visible sunlight, it is incredibly efficient at bleeding internal heat away into the void. It is a technological paradox, a material that looks white to our eyes but acts as a wide-open window for thermal energy to escape. Scientists at the National Science Foundation have determined that the balance between absorptivity, how much heat a material takes in, and emissivity, how much heat it lets out, is the most delicate ratio in all of aerospace engineering. To maintain this balance, engineers use louvers, which are essentially mechanical shutters that open and close over the radiators to regulate the flow of energy. When the spacecraft gets too cold, the shutters close to trap the heat inside, when it gets too hot, they open to reveal the radiators to the dark of space. This mechanical breathing is what allows our machines to maintain a steady internal pulse while traveling through a universe that wants to either melt them or freeze them solid. Have you ever considered the sheer patience required to develop these materials? The glass used in the windows of the International Space Station, for example, is not simple glass, but multiple panes of fused silica that can withstand the impact of orbital debris while blocking the sun's lethal ultraviolet rays. Every gram of these materials must be tested in massive vacuum chambers on Earth, such as the Space Power Facility in Ohio, which is the largest of its kind in the world. There, scientists subject full-size spacecraft to the same 500-degree temperature swings they will face in orbit, ensuring that not a single bolt or wire will fail when the mission finally begins. The data gathered from these tests in early 2026 has led to the creation of even more advanced coatings that can self-heal after being struck by radiation, a technology that was once the stuff of science fiction. Furthermore, we are now beginning to explore the use of phase-change materials in cosmic insulation. These are substances that can store and release massive amounts of energy as they melt and solidify, acting like a thermal battery. Imagine a satellite that soaks up the sun's heat during its journey through the light, storing that energy within a wax-like material, and then slowly releasing that warmth as it passes into the shadow of a planet. This would allow us to build smaller, more efficient spacecraft that do not need as many heavy heaters or complex shutters. It is a vision of a more organic technology, one that moves with the rhythms of the solar system rather than fighting against them. As we look at these shimmering, golden vessels sailing through the dark, it is easy to see them as cold, unfeeling machines, but in reality, they are the most sophisticated garments we have ever woven, a testament to our desire to see what lies beyond our own horizon. We have learned to use the laws of physics against themselves, using mirrors to fight fire and vacuums to fight cold. But as we move further away from our sun, toward the outer reaches of the solar system where the radiation is weak and the shadows are long, the problem of heat changes once again. In the frozen realms of Jupiter and Saturn, the sun is no longer a threat. It is a distant, flickering candle that provides almost no warmth at all. How do we find heat in a place where the sun's bridge has finally crumbled under the weight of distance? What kind of life could possibly survive in the dark, frozen oceans of the outer moons, where the surface is as cold as the void itself? Yet the heart of the world remains warm. This leads us to a stunning discovery in the field of planetary physics, where we find that the wizards of material science are not only human engineers, but the planets themselves. To find the next chapter of our story, we must travel to the frozen hearts of worlds like Europa and Enceladus, where heat comes not from the light above, but from the crushing embrace of gravity below. To understand why we must hunt for the coldest temperatures in the universe, one must first realize that light is not just something we see with our eyes. It is a spectrum of energy that stretches far beyond our biological limits. When we look at the stars, we are seeing the visible light. But the oldest and most distant objects in the cosmos have had their light stretched by the expansion of the universe into a form called infrared radiation. This infrared light is essentially the heat signature of the past. And to see it, a telescope must be capable of detecting a level of energy that is so faint it would be overwhelmed by the warmth of a single human thumb held miles away. This is why the James Webb Space Telescope, a masterpiece of collaboration between the National Aeronautics and Space Administration and the European Space Agency, was designed to be the coldest eye in history. If the telescope were even slightly warm, its own infrared glow would blind it. Much like trying to see the stars while someone is shining a flashlight directly into your eyes. Therefore, The mission of the James Webb Space Telescope is not just a journey of observation, but a journey into the heart of absolute cold, to quest to reach a state where the frantic dance of atoms almost completely stops. To achieve this, the telescope uses a multi-layered defense system that is perhaps the most sophisticated parasol ever constructed. This sunshield is roughly the size of a tennis court and is composed of 5 distinct layers of a specialized material called Kapton, which is a high-technology plastic that remains stable at both extreme heat and extreme cold. It is a staggering thought that each layer is separated by a vacuum of nothingness, ensuring that the heat from the side facing the sun has no physical bridge to cross. Research conducted during the telescope's extended mission in early 2026 has shown that while the side of the shield facing the sun reaches temperatures hot enough to melt lead, the side facing the telescope's sensitive instruments is cold enough to freeze oxygen into a solid. This 300-degree temperature gradient is maintained by a barrier that is, in total, no thicker than a few sheets of paper. Furthermore, it is important to note that the geometry of this sunshield is just as critical as the material itself. Each of the 5 layers is angled in such a way that the heat that manages to bounce between them is directed out the sides and back into the void, rather than toward the telescope. Scientists at the National Aeronautics and Space Administration describe this as a thermal staircase, where each step down reduces the energy by an order of magnitude. By the time the sun's radiation reaches the 5th layer, it has been diluted to almost nothing, allowing the mirrors and cameras to operate in a permanent, artificial night. One must consider the level of precision required to deploy such a structure in the vacuum of space. Over 1 million kilometers away from the nearest human hand, a single snag or tear in those delicate layers would have meant the blindness of our most expensive eye. But for some of the telescope's instruments, even this passive cooling is not enough to reach the silence required for true discovery. While the main body of the telescope sits at a chilly 40 Kelvin, which is approximately minus 233 degrees Celsius, the mid-infrared instrument, often referred to by its full name to avoid confusion, requires a temperature of just 7 Kelvin. This is only 7 degrees above absolute zero, a point where almost all molecular motion ceases. To reach this impossible depth of cold, the telescope carries a cryocooler, a sophisticated refrigeration system that uses gaseous helium to pump heat away from the sensors. This is essentially a high-technology air conditioner that has no moving parts that could vibrate and blur the telescope's vision. It is a silent, constant worker that ensures the instrument remains in a state of cryogenic sleep, allowing it to peer through the thick clouds of cosmic dust that hide the birth of new stars. Have you ever wondered what it means for an object to be at 7 Kelvin? At this temperature, the atoms are moving so slowly that the traditional rules of chemistry and physics begin to shift into the realm of quantum mechanics. It is a place of profound stillness, a sanctuary of cold that allows us to see things that have been hidden since the dawn of time. Because the mid-infrared instrument is so cold, it can detect the heat of distant planets that are not much warmer than our own, allowing us to analyze their atmospheres for the chemical signatures of life. In the last 12 months, data from the James Webb Space Telescope has revealed the presence of water vapor and carbon dioxide on rocky worlds orbiting distant red dwarf stars. Discoveries that would have been completely impossible if the telescope were even a few degrees warmer. It makes one realize that our ability to find life elsewhere in the universe depends entirely on our ability to master the coldest extremes of physics. Furthermore, we must return to the material of the mirrors themselves to understand the full scope of this thermal wizardry. The primary mirror is made of 18 hexagonal segments of beryllium, a metal chosen because it is incredibly stiff and yet very light. But more importantly, because it behaves predictably in the extreme cold. Most materials will warp or shrink unevenly as they cool, which would ruin the telescope's ability to focus light with sub-millimeter precision. However, Beryllium has a low coefficient of thermal expansion at cryogenic temperatures, meaning that once it reaches its operating coldness, it holds its shape with an iron-clad grip. Each of these mirrors is coated in a layer of gold that is only a few hundred atoms thick, specifically designed to reflect 99% of the infrared light that hits it. Scientists believe that this combination of beryllium and gold is the ultimate material partnership for a universe that is mostly cold and dark. As we ponder the achievements of this machine, it is worth asking, what does it feel like to look through an eye that is colder than almost anything in nature? The images sent back to Earth in early 2026 are not just pictures, they are maps of energy, showing us where the universe is warm with the birth of stars and where it is cold with the death of ancient suns. We are seeing a landscape that was previously invisible, a world where the void of space is not just empty, but filled with the glowing ribbons of gas and dust that make up the fabric of our existence. The James Webb Space Telescope has taught us that by embracing the absolute cold, we can see the absolute light. But this hunt for absolute zero also serves as a reminder of how unique our own situation is here on Earth. While we build machines to find the cold, our planet is naturally tuned to a vibrant, warm frequency that is exceptionally rare in the cosmos. We have traveled from the architecture of the vacuum to the survival of the astronaut, and now to the coldest eye of the telescope, always moving further away from the sun's warmth. Yet, even in the furthest, darkest corners of our solar system, where the sun is nothing more than a bright needle prick in the sky, we find that the fire of life has not been completely extinguished. How is it possible that in the frozen realms of the outer planets, where the surface temperature is cold enough to turn air into snow, there are oceans of liquid water that are warmer than the North Pole? What hidden source of energy could possibly replace the sun's bridge of radiation in the deep, dark reaches of the outer solar system? Picture the surface of Europa, a moon of Jupiter that sits nearly 800 million kilometers away from the solar furnace. Here, the landscape is a terrifying wasteland of ice, with temperatures that hover around minus 160 degrees Celsius. A level of cold so absolute that the ice becomes as hard as granite, and the vacuum above is as silent as a tomb. For decades, the consensus among researchers was that Europa was a dead, solid block of frost. However, a series of remarkable discoveries, culminating in data analyzed as recently as early 2026, has peeled back the layers of this frozen mask to reveal a secret of immense thermal power. Beneath a crust of ice that is estimated to be between 15 and 25 kilometers thick lies a global ocean of liquid water, deeper than any abyss on our own planet. This hidden sea contains more than twice the volume of all of Earth's oceans combined, held in a perpetual state of warmth, despite the fact that not a single ray of sunlight has ever touched its surface. The existence of this liquid water in a place so far from the sun seems like a physical impossibility until you account for the invisible, crushing grip of gravity. Europa finds itself caught in a violent gravitational tug-of-war between the massive weight of Jupiter and the neighboring moons of Io and Ganymede. Because the moon's orbit is an elongated ellipse rather than a perfect circle, the distance between Europa and Jupiter changes constantly, creating a rhythmic, tidal force that stretches and compresses the moon's entire structure. Think of the way a piece of thick rubber grows warm to the touch if you bend and pull it repeatedly with your hands. This internal friction, operating on a planetary scale, converts the mechanical energy of gravity into raw thermal energy deep within the moon's rocky core. The core effectively becomes a furnace, heated by the very motion of its orbit, melting the bottom of the ice shell from the inside out. This process of tidal heating represents a total reversal of the thermal hierarchy we experience on Earth. While our world is a top-down system where the sun warms the surface and the atmosphere, Europa is a bottom-up world where the heat rises from the dark, churning heart of the machine. The National Aeronautics and Space Administration has gathered evidence suggesting that this internal fire is likely creating hydrothermal vents on the ocean floor, similar to the volcanic chimneys found at the bottom of our own Atlantic Ocean. These vents spew mineral-rich, boiling water into the dark sea, creating a sanctuary of warmth and chemical energy that could potentially support an entire ecosystem of biological life. The search for extraterrestrial existence has shifted away from a singular focus on Goldilocks zones near stars and toward these gravitational zones, where the embrace of a giant planet provides all the warmth a world needs to breathe. Enceladus, a tiny moon orbiting the ringed planet Saturn, provides an even more dramatic display of this internal mastery, though it is only 500 kilometers in diameter, small enough to be tucked within the borders of a single terrestrial nation. Enceladus is arguably the most thermally active place for its size in the entire solar system. In late 2025 and the opening months of 2026, observations from the James Webb Space Telescope confirmed that this small moon is actively venting massive plumes of water vapor and ice grains hundreds of kilometers into the void through giant, blue-tinged cracks in its southern pole. These tiger stripes are not merely geological features. They are the exhaust pipes of a hidden, pressurized ocean. The heat required to keep this water in a liquid state comes once again from the rhythmic squeezing of Saturn's gravity, which turns the moon's interior into a boiling cauldron protected by a shell of white frost. One of the most profound realizations of material science in this context is that the very ice we perceive as a symbol of death is actually a life-saving insulation blanket, much like the multi-layered foils used on our spacecraft. The kilometers-thick crust of ice on Europa and Enceladus prevents the internal heat from escaping into the absolute zero of the surrounding vacuum, while the surface of the moon radiates its energy away into the dark. The deep water is trapped, held in a pressurized equilibrium that maintains its liquid state for billions of years. The universe has created its own version of a planetary-scale thermos, using the most common material in the outer solar system, water ice, to guard the rarest treasure in the cosmos, warmth. Recent chemical analysis, conducted by the National Science Foundation, has identified phosphorus in the plumes of Enceladus, a discovery that sent shockwaves through the scientific community in the last 12 months. Phosphorus is an essential component of DNA and the membranes of every living cell on our planet, and its presence in a warm, subsurface ocean suggests that these frozen moons possess all the necessary ingredients for life to flourish in total darkness. The old idea that light is the only source of life is being dismantled, replaced by a new understanding that gravity and friction are equally capable of nurturing the fire of existence. We are learning that the universe is not a barren wasteland with a few lucky islands of warmth, but a place filled with secret gardens hidden beneath shells of granite-hard ice. As we dwell on these hidden oceans, a sense of wonder arises at the thought of what might be swimming in those lightless depths. A creature born in the seas of Europa would have no concept of a sun, no understanding of stars, and no word for the color blue. Its entire universe would be defined by the rhythmic pulse of Jupiter's gravity and the gentle, rising heat of the hydrothermal vents. This existence is a testament to the resilience of energy, proving that warmth is not just a gift from above, but a consequence of the very motion and mass of the cosmos. The cold of space is merely a quiet backdrop against which the universe performs its most ingenious tricks of heat generation. The National Aeronautics and Space Administration is currently preparing the Europa Clipper mission, a sophisticated scout scheduled for arrival in the Jovian system in the early 2030s. This spacecraft will carry ice-penetrating radar and thermal images to map the moon's hidden currents and identify the places where the internal heat is closest to the surface. We are on the threshold of finally seeing through the ice, peering into a world that has remained a mystery since the dawn of the solar system. Every measurement we take in the coming years will refine our understanding of how a world can stay warm when it is nearly 1 billion kilometers away from its star, revealing that the frozen hearts of these moons are actually the most vibrant places in the outer dark. Yet, even as we uncover these pockets of local warmth, the larger question remains unanswered. We have seen how heat can be manufactured by the friction of gravity and preserved by the insulation of ice. But these are small, isolated victories against an overarching cold that seems to define the very fabric of space. Why is the baseline temperature of the universe not 0, but -270 degrees? Why is there a faint, ghostly warmth that permeates even the emptiest voids between the galaxies, far beyond the reach of any star or moon? To find the ultimate context of our story, the focus must shift away from the planets and toward the Trotan of creation itself. The ancient echoes that still whisper through the dark. We are living in the cooling embers of a much greater fire, a cosmic event so vast that it defined the thermal boundaries of everything we see today. The warmth we feel from the sun and the friction of the moons are merely temporary ripples in a much larger, older ocean of energy that has been cooling for nearly 14 billion years. The final mystery lies in the very first light that ever traveled through the void, a light that holds the secret of why the universe is as cold as it is, and why it was once infinitely hot. Every cubic centimeter of the void, no matter how remote or empty it may seem, is saturated with a faint glow of energy that researchers call the cosmic microwave background radiation. This pervasive light is the oldest thing anyone can ever see, a relic from a time when the entire universe was a roiling, opaque sea of white-hot plasma. During the first 380,000 years after the beginning of time, the cosmos was so hot and so dense that light could not travel through it. Photons were constantly bumping into free electrons, trapped in a chaotic fog that made the universe a brilliant, impenetrable soup of energy. Only after the universe had expanded and cooled to a temperature of approximately 3,000 degrees Kelvin could the first atoms begin to form, a process known as recombination. In this pivotal moment, electrons were finally captured by protons to create neutral hydrogen, suddenly clearing the cosmic fog and allowing the first light to break free and travel across the darkness. This first light has been traveling through the expanding void ever since, but its journey has fundamentally altered its character, because the space through which these photons travel is constantly stretching. The light waves themselves have been pulled and elongated over billions of years, a process known as cosmological redshift. What began as a blinding, white-hot glare has been stretched into the longer, invisible wavelengths of microwaves, losing almost all of its energy in the process. Today, the National Aeronautics and Space Administration and the European Space Agency have determined that this ancient light has cooled to a staggering 270 degrees below 0 Celsius, or roughly 2 Fabe degrees above absolute zero. This temperature represents the baseline of the universe, a thermal floor below which nothing can naturally fall, serving as a permanent reminder that we are drifting in the aftermath of a monumental explosion. The discovery of this cosmic glow is one of the most compelling stories in the history of science, involving two researchers in New Jersey back in the mid-1960s who were troubled by a persistent hiss in their radio antenna. Arno Penzias and Robert Wilson initially suspected that the interference was caused by pigeon droppings on their equipment, but after meticulously cleaning their instruments and ruling out every terrestrial source, they realized they were listening to the heartbeat of the universe itself. This hiss was the sound of the Big Bang, a thermal signature that was coming from every direction in the sky with perfect uniformity. Their accidental discovery provided the first definitive proof that the universe had a beginning and that it has been cooling ever since. A revelation that earned them the Nobel Prize and forever changed our understanding of the cosmic timeline. Recent observations from the Atacama Cosmology Telescope in late 2025 and the ongoing analysis of data from the Planck satellite have provided us with a map of this ancient glow that is more detailed than anything previously imagined. These maps reveal tiny, microscopic fluctuations in the temperature of the cosmic microwave background, differences of only a few millionths of a degree, which represent the original seeds of gravity. These minute ripples in the thermal fabric of the early universe are the reason why galaxies, stars, and eventually human beings exist at all without these tiny variations in heat. The universe would have remained a smooth, featureless gas, never clumping together to form the structures we see today. It is a staggering thought that the very cold we feel when looking into the night sky is the same energy that dictated the distribution of every sun and planet in existence. Furthermore, a deeper look at the mechanics of this cooling reveals a growing mystery that cosmologists refer to as the Hubble tension. In early 2026, refined measurements of the expansion rate of the universe have suggested that the cosmos is growing faster than the ancient light of the cosmic microwave background predicted it should. This discrepancy suggests that there may be a missing piece in our understanding of how heat and energy behave on a universal scale, perhaps involving a form of dark energy that behaves differently than previously modeled. The universe is not just cooling, it is doing so in a way that suggests the laws of physics might have changed over the billions of years since the first light was released. This tension is currently the most significant debate in the field of cosmology, a puzzle that forces us to question the very nature of the vacuum and the energy it contains. By examining the furthest reaches of the sky, we also find that the temperature of the void is not perfectly uniform. There are vast regions known as voids, where almost no galaxies exist. And in these places, the temperature can drop even closer to absolute zero. The most famous of these is the Boötes void, a terrifying expanse of nothingness that is hundreds of millions of light years across. Within these dark cathedrals of space, the silence is so profound that the only thing left is the ancient 2.7-degree whisper of the Big Bang. One might feel a sense of insignificance when contemplating these scales, but it also highlights the incredible rarity of our own situation. We live in a pocket of the universe that is billions of times hotter than the background, a local anomaly created by the concentrated energy of our sun. A fundamental realization that arises from studying this ancient light is that the universe is essentially a cooling engine. Every star that burns and every galaxy that rotates is slowly contributing to the inevitable increase in entropy, a process where energy becomes more and more spread out until it can no longer be used to do work. The warmth we feel today is a temporary state, a brief flicker of heat in a story that began in infinite fire and will likely end in infinite cold. However, this overarching chill is also what allows for the complexity we see around us. If the universe had remained as hot as it was in the beginning, atoms could never have formed, and the light of the stars would never have reached our eyes. The cold is the stage upon which the drama of life is performed, providing the necessary contrast for energy to flow and for work to be done. The National Science Foundation continues to fund massive observatories at the South Pole, where the air is the clearest and driest on Earth. To study these microwave signals with even greater precision, these researchers are looking for B-mode polarization, a specific twist in the ancient light that would provide evidence for gravitational waves from the very first fraction of a second of the Big Bang. If detected, these signals would allow us to see even further back in time than the first light of the cosmic microwave background, peering into the moment when the universe was only a trillionth of a trillionth of a trillionth of a second old. At that moment, the temperature was so high that all the forces of nature were unified into a single, supreme power. Our current cold universe is merely the distant, quiet shadow of that original. Perfect symmetry, One of the most beautiful aspects of this thermal history is the realization that every human being is carrying a piece of this ancient fire within them. The atoms in our bodies were forged in the hearts of stars that used the cooling gas of the Big Bang as their raw material. We are, quite literally, the universe experiencing its own cooling. A collection of atoms that have learned how to maintain a steady temperature of 37 degrees Celsius in a cosmos that is trending toward the absolute zero of the void. The struggle of our ancestors to find fire and the struggle of our engineers to insulate our spacecraft are all part of the same cosmic narrative. The attempt to preserve warmth in a universe that is slowly but surely letting its energy fade away. This global perspective on heat and cold helps us realize that our planet is not just a rock orbiting a star, but a delicate balance of energies that have been in motion since the dawn of time. We have seen how the vacuum insulates, how radiation bridges the gap, and how the ancient echoes of the Big Bang set the stage. But even with all these universal laws in place, why is Earth so perfectly tuned for life while so many other worlds are either scorched or frozen? The bridge of radiation and the echoes of the past provide the materials, but it is the Goldilocks zone that determines how those materials are used to create a living world. The boundaries of this thermal sanctuary are far more fluid and dangerous than a simple map of the solar system might suggest. As the fate of our neighboring worlds, Venus and Mars, provides a grim testament to how easily a planet can slip into a state of total environmental collapse. Venus, our twin in terms of size and mass, sits only about 42 million kilometers closer to the Sun than we do. Yet, it has become a literal hellscape, where the surface temperature remains a constant 460 degrees Celsius, hot enough to melt lead and turn any visiting spacecraft into a puddle of molten metal within minutes. Scientists at the National Aeronautics and Space Administration have determined that Venus once possessed oceans of liquid water, but because it sat just slightly too close to the solar furnace, a runaway greenhouse effect took hold. The sun's radiation evaporated the water, which subsequently acted as a powerful heat-trapping gas, leading to a feedback loop where the planet grew hotter and hotter until the very rocks began to bleed carbon dioxide into the air. Today, the Venusian atmosphere is 90 times thicker than Earth's, a crushing blanket of carbon dioxide and clouds of sulfuric acid that ensures no heat can ever escape, creating a world where the bridge of radiation has become a one-way street into an incinerator. In stark contrast, Mars represents the opposite tragedy, a world that had the potential for warmth but lacked the material strength to hold onto it. Mars sits about 78 million kilometers further away from the Sun than Earth, placing it on the outer edge of the habitable zone, where it should, in theory, be able to maintain liquid water if it had a thick enough atmosphere. However, because Mars is much smaller than Earth, its internal core cooled down much faster, leading to the death of its magnetic field billions of years ago. Without this invisible shield to deflect the solar wind, a stream of charged particles from the Sun, the Martian atmosphere was slowly stripped away and lost to the vacuum of space. Research conducted by the MAVEN mission and updated with findings in early 2026 confirms that Mars is now a frozen desert, where the air is so thin that liquid water would instantly boil away into gas before freezing into ice. It is a haunting reminder that a planet must not only be at the right distance from its star, but it must also possess the geological heart to sustain a protective cloak. The Earth, positioned precisely between these two failures, utilizes a sophisticated planetary thermostat that has kept our temperature stable for nearly 4 billion years, even as the Sun has grown approximately 30% brighter since the dawn of our solar system. This thermostat is driven by a process called the carbon silicate cycle, which involves the movement of carbon dioxide between the atmosphere, the oceans, and the Earth's interior through the action of plate tectonics. When the planet becomes too warm, Increased rainfall washes carbon dioxide out of the air and into the rocks of the sea floor. When it becomes too cold, volcanic activity releases that trapped gas back into the atmosphere to thicken our insulation blanket. Have you ever considered the staggering fortune of living on a world that can effectively think for itself, adjusting its own material composition to ensure that the liquid water required for life never vanishes? It is a slow, rhythmic breathing of a planet that has mastered the art of thermal regulation on a global scale. Furthermore, the material science of our surface plays a critical role in maintaining this balance through the concept of planetary albedo, which is the measure of how much solar radiation a world reflects back into the dark. If the Earth were covered entirely in dark forest or open ocean, we would absorb so much heat that our polar caps would melt, leading to a much warmer and potentially unstable climate. Conversely, if we were covered in too much ice, the white surface would reflect nearly all of the sun's energy back into space, triggering a snowball Earth scenario where the entire planet freezes over. In late 2025, satellite data from the European Space Agency revealed that the rapid loss of Arctic sea ice is significantly lowering our planet's albedo, causing the dark northern waters to absorb heat at an accelerated rate. This shift reminds us that the Goldilocks state is not a permanent gift, but a dynamic equilibrium that can be tipped by even a small change in the materials that cover our surface. One must also look toward the recent discoveries made by the James Webb Space Telescope to understand just how diverse these habitable worlds can be. In the last 12 months, astronomers have identified a new class of planets called Hycean worlds. Large, rocky planets covered in global oceans and surrounded by hydrogen-rich atmospheres. These worlds, such as K2-18b, could potentially maintain liquid water much further away from their stars than Earth can, because hydrogen is a much more effective greenhouse gas than nitrogen or oxygen. This discovery has expanded our definition of the Goldilocks zone, suggesting that warmth can be found in places we once thought were too cold for life. However, these worlds also face their own thermal challenges. A hydrogen atmosphere is incredibly light and can be easily stripped away by the radiation of a young, violent star, leaving the planet as a naked, frozen rock. It seems that wherever we look, the struggle to maintain heat remains the central drama of the universe. Scientists at the National Science Foundation are currently debating whether a planet's moon might also play a role in its thermal stability. Our own moon is unusually large relative to our planet, and its gravitational pull creates the tides that help distribute heat throughout our global oceans. Furthermore, the moon's gravity stabilizes the Earth's tilt, ensuring that our seasons remain relatively mild over millions of years. Without this gravitational anchor, the Earth might wobble wildly on its axis, causing the poles to occasionally point directly at the sun and then away into the darkness, leading to extreme temperature swings that would make the evolution of complex life nearly impossible. Is it possible that the perfect temperature for life requires not just a star and a planet, but a celestial partner to keep the rhythm steady? Beyond the physical distance and the atmospheric composition, there is the question of the star quality itself. Most of the stars in our galaxy are red dwarfs, which are much smaller and cooler than our Sun. To be in the Goldilocks zone of a red dwarf, a planet must orbit incredibly close, so close that it likely becomes tidally locked, with one side always facing the star and the other always facing the dark. This creates a world of two halves: a permanent, sun-scorched desert on one side and a permanent, frozen wasteland on the other. For such a world to be habitable, its atmosphere must be thick enough to carry heat from the day side to the night side, creating a narrow ring of twilight where the temperature is just right. Researchers studying the TRAPPIST-1 system in early 2026 have noted that these planets are essentially thermal tightropes, where the margin for error is almost non-existent. A profound realization arises when we consider the sheer number of variables that must align to create a world like ours. You need the right kind of star, the right orbital distance, a planet with enough mass to hold an atmosphere, a molten core to generate a magnetic field, and a chemical cycle to regulate the greenhouse effect. When you add up the odds, the warmth we experience every day begins to feel less like a mundane fact of nature and more like a rare, precious anomaly in a universe that is overwhelmingly indifferent to our survival. We are the residents of a cosmic oasis, a tiny, vibrant island of 37 degrees Celsius, biological life floating in a sea of minus 270 degrees Celsius nothingness. As we ponder our place in this thermal sanctuary, it is worth asking how much longer this balance can last. We know that the sun is slowly getting brighter and hotter as it ages, and in about 1 billion years, it will become so intense that the Earth's oceans will finally boil away. Following the tragic path of Venus, we are living in the middle of a glorious, multi-billion-year afternoon. But the shadows are eventually going to grow long. Does this make our current warmth more meaningful? Knowing that it is a temporary state in the grand timeline of the cosmos, this perspective shift forces us to move beyond our local concerns and look at the ultimate destiny of heat itself, the transition from the vibrant warmth of a living world to the cold, dark future of the cosmos is the most profound perspective shift of all, carrying us from the comfortable Goldilocks present to a future where the very concept of a temperature zone becomes meaningless. Every star that burns in the night sky and every sun that warms a planet is essentially a finite battery, a localized concentration of energy that is slowly but surely being drained into the infinite reservoir of the surrounding void. A fundamental principle of physics known as the second law of thermodynamics dictates that in any closed system, energy will always spread out from where it is concentrated to where it is sparse, moving toward a state of perfect, uniform disorder called entropy. On a cosmic scale, this means that the heat of the stars is destined to flow into the cold of the vacuum until the two are no longer distinguishable, leading to a final state of existence that scientists call the heat death of the universe. The current age of the universe, which astronomers refer to as the stelliferous era, is a brief and glorious window of time characterized by the brilliant light of burning suns and the formation of complex galaxies. We find ourselves living in a moment of extraordinary abundance, where the bridge of radiation is still strong and the cosmic baseline is still warm enough to allow matter to clump together into planets and people. However, research conducted by cosmologists at the National Science Foundation in early 2026 suggests that this era of light will eventually come to a close as the supply of primordial hydrogen is exhausted. When the last gas clouds are consumed and the final stars flicker out, the universe will enter the degenerate era, a long twilight where the only remaining light comes from the cooling embers of white dwarfs and the faint, ghostly glow of neutron stars. In this distant future, the temperature of the cosmos will continue to drop, moving closer and closer to that absolute zero. We have spent so much of our journey discussing, one might find it difficult to grasp the timescales involved in this thermal decline, as the death of the last star will not occur for another 100 trillion years, a number so vast that it represents more than 7,000 times the current age of the entire universe. During this immense span of time, the galaxies will slowly drift apart due to the influence of dark energy, which acts like a cosmic anti-gravity that stretches the fabric of space at an ever-accelerating rate. Scientists at the European Space Agency have determined that this expansion will eventually become so fast that the light from neighboring galaxies will be unable to reach us, leaving every star system as a lonely island of fading heat in an infinite sea of darkness. The bridge of radiation that once connected the cosmos will finally be broken, not by the vacuum itself, but by the sheer speed of the universe's growth. Furthermore, the transition into the black hole era presents a landscape of even more profound thermal isolation, where the only large-scale structures left in the cosmos are the gravitational abysses that once sat at the centers of galaxies. For an inconceivable amount of time, measured in numbers, followed by over 100 zeros, these black holes will be the masters of the universe, slowly swallowing the cold, dead remains of stars and planets. But even these giants are not eternal, as a process known as Hawking radiation ensures that even a black hole will slowly lose mass and energy over time. Research into the quantum mechanics of the event horizon indicates that black holes leak energy back into the void at an agonizingly slow pace, eventually evaporating in a final, brilliant flash of gamma rays. When the last black hole vanishes, the universe will lose its final source of concentrated energy, leaving behind nothing but a thin, freezing mist of subatomic particles, the final state of existence, which represents the ultimate resolution of the paradox of heat and cold, is the dark era. At this point, the universe will have reached a state of maximum entropy, where the temperature is perfectly uniform across every billion light-years of empty space. There will be no more suns to provide warmth, no more planets to catch the light, and no more internal fire within the hearts of moons. The temperature will have settled at the absolute floor of physics, just a fraction of a degree above absolute zero. But because there will be no temperature differences anywhere, no work can ever be performed, and no information can ever be processed. This is the heat death, not a death by fire, but a death by the total absence of energy flow. It is a state of perfect, frozen equilibrium, where the architecture of nothingness has finally won its long battle against the light. Scientists believe that the accelerating expansion of the universe, confirmed by refined measurements of the Hubble constant in the last 12 months, makes this cold conclusion almost inevitable. We are living in a universe that is being torn apart by its own growth, a process that ensures that every source of heat will eventually be isolated and extinguished. Furthermore, it should be noted that this perspective shift changes the way we value the cold of space today. In our current era, the cold of the vacuum is a necessary contrast that allows the heat of the sun to move and create life. It is the sink that allows the solar engine to run. Without the profound cold of the void, the sun's energy would have nowhere to flow, and the delicate dance of thermodynamics that sustains our world would grind to a halt. The cold is not the enemy of life, but its essential partner. Have you ever considered that the warmth you feel from a simple cup of tea or the heat of your own skin is a tiny, localized rebellion against the inevitable trend of the universe? Every time we light a fire or build a radiator, we are briefly reversing the flow of entropy, creating a pocket of order in a cosmos that is slowly trending toward disorder. This realization brings a profound sense of gratitude for the now, for this specific moment in the cosmic timeline when the sun is still hot and the stars are still bright. We are the witnesses of the universe's most vibrant hour, a brief and beautiful period where the laws of physics allow for the existence of complexity and consciousness. Furthermore, recent theoretical models, proposed in early 2026, suggest that even the heat death might not be the absolute end of the story. Some physicists at the National Aeronautics and Space Administration and various international research institutes are exploring the possibility of quantum tunneling events that could, over unimaginably long periods of time, trigger a new Big Bang or a local inflationary event. This would suggest that the universe operates in cycles of heat and cold, a rhythmic breathing that spans trillions upon trillions of years. However, even in these models, the current era remains a unique and precious window, a summer that will eventually give way to a winter longer than the human mind can possibly imagine. As we draw our journey to a close, the mystery of why space is so cold when the sun is so hot reveals itself to be the story of our own existence. Space is cold because it is empty, and it is empty so that the light of the stars can travel. The sun is hot because it is a concentration of the universe's original energy, a fire that is slowly spreading its warmth across the dark. We sit in the middle of this exchange, protected by 14 layers of fabric, 5 layers of gold-coated plastic, and a fragile blue blanket of air. We have seen how the vacuum acts as a shield, how radiation acts as a messenger, and how the gravity of giants can turn a frozen moon into a hidden garden. We have listened to the echoes of the past and peered into the silence of the future, always returning to the same truth. The warmth of our world is a fragile, temporary miracle. One must realize that the cold we fear is actually the silence that allows the song of the sun to be heard. If the universe were filled with heat, there would be no shadows, no seasons, and no life. The cold is the canvas, and the light is the paint. Without the one, the other would be invisible. As you sit in the quiet warmth of your own room, perhaps feeling the steady rhythm of your own heart or the gentle weight of the air around you, you are experiencing the culmination of 14 billion years of thermal history. You are a creature of the sun, living in a house built by the vacuum, listening to the fading whispers of the beginning of time. This understanding provides a final perspective shift that is both humbling and empowering. We are not just victims of the cold or beneficiaries of the heat. We are the observers who give meaning to both. The fact that we can even ask why the sun is hot and space is cold is a testament to the incredible complexity that has emerged from the simple movement of energy. As the stars continue their long, slow burn, and the galaxies continue their silent drift, we can take comfort in the knowledge that we are part of a narrative that is as vast as the void and as intense as the solar fire. The heat of the sun will eventually fade, and the bridge of radiation will eventually collapse. But for this moment, right now, the fire is burning bright, and the world is warm, and that is enough. The story of the universe's temperature is ultimately a story of balance. A balance between the infinite energy of the past and the infinite silence of the future. We live in the middle of that balance, in a small, beautiful pocket of 37 degrees Celsius, looking out at a universe that is nearly 300 degrees colder than we are. And in that contrast, we find our home,